Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Alexis Rodriguez with us today. Hello, Alexis.
Hello, thank you for having me in your show.
Well, thank you so much for agreeing to talk about your very lovely article. And Alexis,
Thank you.
Where are you located at?
I'm right now in Huntsville, Alabama, at the Marshall Space Flight Center.
Very cool. And it is November 30th of 2023 as we record this. And has winter hit Alabama yet?
It has, but actually the weather is really nice. Really enjoying it after spending a really hot summer in Tucson, Arizona. We had an extremely dry and hot summer.
Yes. So I'm in Phoenix. So normally we would be separated by about
it's
100
nice
miles
to be in the fresh winter after spending time over 100. So
Indeed. Yes. And Alexis.
So where are you?
So I'm in Phoenix.
Where are you actually?
Phoenix?
Oh, Phoenix, Arizona. All right, so you
I'm
understand
Phoenix.
what I'm talking
So
about.
I'm only about normally 100 miles from you, so we kind of share the same weather. Although it is a little bit hotter in Phoenix than it is in Tucson. So
I know.
Yeah. But yeah. And so Alexis, what do you like to do for research?
Well, just as a background, I spent most of my career investigating Mars, the hydrology of Mars.
Cool.
And something that, always fascinated me was the evolution of the Martian hydrosphere. The fact that on Earth, we have this integrated hydrosphere connecting surface water and subsurface water environments. On Mars, we had a similar hydrosphere about before 3.7 billion years ago, but then it diverged and most of the water went into the subsurface.
Yes.
More recently, I've been working on Mercury and the origin of the
Oh.
volatile rich crust, which is what we're going to be talking about. And here at the Marshall Space Flight Center, and I just started a position here now, and I'm involved in looking at areas of recent lunar seismicity.
Oh, cool.
So kind of pretty diverse. I'm looking at a lot of different topics, but all connected to space.
Lots of topics are good. Very cool.
Yeah.
And that is going to bring us to this very awesome PSJ article. Bring this up. There we go. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Mercury's hidden past, revealing a volatile-dominated layer through glacier-like features and chaotic terrains. And Alexis, take us away.
Okay, first of all, I have to acknowledge, my co-authors, it's an awesome group of co-authors, and without them, this paper would have not been possible, so it's really like a team effort. I'm not going to read all their names because it would take a while.
Shout out. That's a good
yeah, but they did incredible work. So I guess that if you want me to get started on the paper and the science,
yes,
maybe we can go and take a look at the first figure in the supplementary materials where we see the hollows.
First figures.
So we're going
supplementary.
in the supplementary.
Hold on. Look at there. Here we go. A1.
Yeah. So the reason why I wanted to show this figure first is because you see the scale there is 5 kilometers. So it's a very high resolution view of the surface of Mercury. So this is a discovery, okay, that was done by other teams, and the finding of hollows, these depressions are called hollows. They look very similar to sublimation pits on Earth.
Okay.
Very similar to thermal karst features, and they were interpreted right away as evidence of a volatile rich layer on the surface of Mercury. Something that you'll notice is that they form dense clusters. You can see how these, these in the color image here, the blue areas, these are the hollows, and they are clustered, and mostly they occur within impact craters. That's their predominant distribution, as far as I know,
Flat.
and they are very widespread throughout the planet. Yet, because they are so small, the total surface area of these features, is minimal. Is like, I mean, as they've been mapped, they don't really represent aerially. They don't represent. They're not representative of like the Mercurian surface because it's a very small percentage,
Okay.
as far as the area they cover goes. So, uh, so like the discovery of hollows like represents a major paradigm shift because people used to think that Mercury was like bone dry, like no volatiles at the surface.
Yes.
Like compare it to the moon. Like people thought that possibly was very similar in that sense. And it kind of like makes sense because Mercury is very close to the sun.
Right.
So like any volatiles in the solar nebula during its formation would have been driven away. That's what you would have thought was most likely to be the case. So this constitutes a departure, but it also brings up like some like major enigmas, right? And one of them is, right, so how characteristic is this volatile rich crust of Mercury, and like how deep is it?
Yeah.
Okay.
Yeah.
So like, because like these features, like they range from a few tens of meters to over 100 meters deep. That's not very deep,
Okay.
in terms of like the thickness of the crust.
Oh, yes.
So like
But
so that's like a major question because you could have a volatile rich layer that experiences localized disturbances. Okay, but then has like a self-stabilizing mechanism. So like the depths of sublimation might not be representative of the depths of the volatile rich crust.
Okay.
Okay, so the volatile rich crust could be a lot deeper. Like if you go to like an Earth glacier, you could have like sublimation depressions, right? Or melt depressions
Yes.
that don't reach the base of the glacier.
Okay.
Still they're pitted and they have like, irregular, shapes, like very similar to this here. So or like permafrost. So then like if we could take a look at the chaotic terrain view that I mentioned in the press release, the chaotic terrain on Mercury.
We're going to do a little shift here, people. Hang on a second, and we are going to cover a little bit of chaotic terrain.
Oh, that's like the Mars one, like the Mercury one. Yeah, there is another link that I shared.
I have the sun
So, okay, so then like all right. So maybe, can you like scroll down on the
this one?
So I guess that we can, yeah, no, that's like the Mars one. But anyways, I can talk about it if we don't find it. It's totally okay. So chaotic terrains are essentially areas of major surface collapse where like heavily cratered terrains appear to be broken into like knobs and mesas, and they are characteristic of Mars. And they normally happen. This is an example of a chaotic terrain on Mars, by the way. So it actually serves the purpose. It's like an oblique view of a chaotic terrain on Mars. So, so what happens is that they've been mostly studied on Mars, like although they do happen in other planets, like on Mercury. And on Mars, and I'm going to talk a little bit about Mars now because it's essential to understand the connection to Mercury here.
Okay.
So on Mars, the chaotic terrains, like have for decades now, have been considered to represent areas where there were aquifers. Okay. Now, the aquifers became unstable and they released their groundwater to form like very large flats. And like the evacuation process produced like a surface instability that led to the collapse and subsequent, leading to the formation of these features. Now, why I'm saying this is because this very simple description is a cornerstone, hypothesis to most of what we think of like Mars hydrology, because it's like revealing or suggesting that Mars had a major surface hydrology,
Yes.
like a hydrosphere, subsurface hydrosphere that then became connected to the surface, via these features. So chaotic terrains on Mars, might actually represent windows
Cool.
interconnecting a volatile rich, crust, an aquifer crust to the surface. Now,
Cool.
on Mars, they are connected to outflow channels, and the outflow channels connect to like the northern plains where we think the floods produced an ocean. Going back to Mercury, we have very similar terrains, very similar chaotic terrains.
Yeah, as we
In
saw.
fact, unless
Mhm.
unless you've spent a lot of time, examining the chaotic terrains of Mercury, you might actually think that you're looking at Mars. That's how similar they are, the chaotic terrains themselves. I mean, there are differences, but you've got to be, like familiarized with both landscapes to know them. Now, the the chaotic terrain, like there is a very large chaotic terrain on Mercury, that has been known since 70s, and there was a hypothesis that it was called the weird terrains, by the way.
Very technical term there.
Yeah, yeah. So the hypothesis for this chaotic terrain was that like the formation of the Caloris Basin due to like an asteroidal impact. Uh, this is a very large basin, okay, over 1,000 kilometers across, I think.
Yes.
It produced seismic waves,
Yes.
like body seismic waves and surface seismic waves that
Yes.
traveled through the surface and through the interior of the planet and then converged on the other side of the planet.
Antipodal.
Yeah, the antipodal area. This would have produced like enormous seismicity, like disrupting the landscape.
Yes.
But on top of that, you had the ejecta from the Caloris Basin coming in as projectiles,
Okay.
like from everywhere, and
Yep.
the ejecta would have covered, all the plains in between the crater rims that were seismically destroyed. Okay,
Yes.
so that was like the view that persisted until 2020 when we published an article in scientific reports. And the article actually shows that the origin of this chaotic terrain was not connected to the Caloris impact.
Okay.
Basin. Okay. So first of all, we did crater counts and we found that is 1 billion years younger, the chaotic terrain.
Ooh,
So
okay.
1,000 million years, like younger, right? So, and then there are key observations, like morphologic observations, that are inconsistent with the seismicity and ejecta deposition hypothesis. One that I find really interesting is that the chaos, right, does disrupt like large impact craters, but it also modifies craters that are very small, okay, like 10 kilometers in diameter.
Okay.
Yeah.
Okay. Yes. Yes.
And like, yeah, so that's actually a fundamental observation because
Yes.
you see, if you had this massive seismicity capable of destroying the large craters, the small ones, sayonara, right?
They're gone.
They'd be gone. And then like you would have the ejecta coming in and burying whatever was left,
Yes. Yes. I'm with you.
So that's a case for like the Ingenie terrains on the moon. I think they're called Ingenie.
Ooh.
Yeah.
Yes.
So then like what we actually found is that this chaotic terrain of Mercury shows evidence of relief loss. Okay, that's very important. So, for example, there are multiple rims that are dissected, or they show like basically gaps, like linear gaps in their, in their surfaces.
Yes.
And these are not due to like superposition. It's actually the removal of rich material, producing these lineated patterns that then break up the terrain.
Okay.
So that led us to the hypothesis that, maybe we're looking at a volatile rich crust of Mercury.
Ooh.
And that the chaotic terrains are kind of like,
reflection,
like the evidence
for
like the volatile losses from this upper crust.
Cool.
Then what we found in 2020 as well is that there are many chaotic terrains on Mercury, not just one.
Good.
And that kind of like brought up the question:
Good.
are we looking at a volatile ridge crust, or is it
Exactly.
localized?
Exactly.
So now, then we go back to our article,
Okay.
now that we have the key questions, and then we go to figure 1.
Okay. Figure 1. Let's slide over up to figure 1, the polar region. There we go.
Yeah. So I just mentioned that. Do you want to zoom into the figure?
Yep.
So I just mentioned that there are multiple chaotic terrains on Mercury, right? In that, one that is, in my view, perhaps the most important one scientifically, is Borealis chaos.
Yep.
You can see that it actually reaches the North Pole, and we'll go into it later. We're going to talk about this chaotic terrain because its morphology carries some fundamental science.
Cool.
Then, you can also see in this figure the location of the Radilati crater.
Yes.
And the Eminescu crater.
Mm-hmm.
I always have difficulty pronouncing these names.
But you did pretty good. You did better than I would do.
I don't know who chose them, but anyways, these two impact craters are craters where we found evidence of possible glaciers. So let's go to figure 2B.
2B. And we're going to slide on down to B.
Yeah, so there, yeah. So this, well, you can see in figure 2A that, it's in the view as well. So all the area that is shaded in red are basically these lobate features that we interpret to be glacier residues or glaciated flows, right? Okay. Now, the yellow dots are on these red surfaces are hollows or sublimation pits.
Cool.
Now, something to note here is that these lobate features only happen around this peak ring in the center of the crater. Okay, so when you look at the crater wall, you don't see them. Okay, and these lobate features extend from the peak ring itself exhibits hollows, evidence of sublimation. And but what really caught my attention was the fact that you have a lot of superposed hollows on top of this lobate feature.
Right.
Okay.
Right.
You see the red arrows there, and the white arrows indicate the frontal margins. As they superpose the crater floor. Now, the hollows, on top of these materials imply that they have a volatile rich composition. Okay, and the flow morphology would be consistent with a glaciated flow. We did some numerical modeling, and the modeling suggested that halite, is a good candidate. Remember, something that I mentioned here, okay, is that these flows are extending from the peak ring, from the ridges. Okay, so maybe if we go to the panel C there, maybe we can see that better.
C, this is going to get us, yes.
Yeah. Yeah, all right. So, this panel here shows the topography that's been removed from the flows, due to the hollows. So that's what I was saying, that the flows, these deposits, they are very volatile rich, and the volatile composition seems to be almost the same in some locations as the thickness of the materials.
Okay, good.
So can we go to figure 3?
Sure, I'm with you.
It's to show
figure 3.
I just want to show what the concept here is. All right, so I was mentioning, if we look at panel A, so the ridges, you have areas where you have very extensive hollows. Look at, in panel A, where I have the red arrow there.
Yeah.
You can see that the top of the ridge is almost being truncated. In the topography, it appears almost flat. So so one possibility here is that the materials flowed away from the ridge to form these lobate lobate flows. Okay, so now okay, so if we go to figure supplementary, the second figure in the supplementary materials.
Sure. Hang on one sec. Let me get there. 1, 2. There we go.
Oh yeah. So this is a comparison between like the flow morphologies and like similar features on Mars in B that are thought to be debris-covered glaciers, extending as well from like the promontory stratigraphy. And then in C, you have a salt glacier extending from a salt extrusion in the Zagros Mountains, in Iran.
Yeah.
So, oh right, yeah. So I knew that I was forgetting to say something here. So, like something important here is that these glaciers extend from like exposed stratigraphy.
Yes.
Okay, I suppose they are not like the glaciers, like the alpine glaciers, where you have like snow accumulation.
Yeah.
Okay,
Yeah.
and and then crystallization and then gravity-driven flow. These
Right.
are materials that are coming from a volatile-rich stratigraphy.
Cool.
For in the case of Earth, for the Zagros Mountains, they extend from diapirs. In the case of Mars, they probably extend from permafrost, at least in some cases. And in the case of Mercury, from these peak rings. Okay. Now, I did mention that
Cool.
we did some modeling. Like actually, Brian Travis, one of the co-authors, like did the modeling, and the modeling was like really interesting because it did find that halide as a salt component, as a dominant salt component, would have, generated the kind of viscosity and flow rates that would be typical of glaciers.
Yeah.
And
Cool.
also like they would explain the formation of the hollows,
Sure. Boom.
and yeah, and being like a volatile type of material on the surface of Mercury.
Cool.
So
Cool.
yeah, I think I'm just trying to think whether I'm forgetting anything here. All right, so let's talk a little bit about like the implications towards the volatile rich crust here. So let's go to figure 8. I think it's like the sketch, where we have the sketch with the stratigraphy.
One sec. Figure 8. There we go. Figure 8.
Oh no, sorry. So it's gonna be like figure 10. Sorry.
10. All good.
Figure 10. Right.
All good.
Yeah.
There we go. This one.
Yeah. So yeah, here. Yeah, this one.
Yeah,
So like I want to show this now because we've already like talked about a lot of different things here. So the initial concept from the 2020 paper is that we had a volatile rich crust over a buried crater surface. Okay. Now what I think we are seeing here, like what we have chaotic terrains localized in some areas, and then we have these glacier-like features, extending from crater interiors, and promoting the formation of hollows on their surfaces, is because like very early in the history of Mercury, we could have had like the following evolution. So B here, like panel B, shows like a testable hypothesis, but I think is a very important one. Like areas where the volatile rich crust, the volatile rich layer, would be exposed at the surface,
correct,
like to the left,
right.
And areas where it would be covered by lavas,
right over here.
Okay.
Yes.
Right to the right. Then, like having this stratigraphy is the departure point to, seeing areas where you have these impacts, exhuming the volatile rich layer, like into the peak rings, and then like producing these glacier-like flows, that maybe salt flows, if that's a composition. Then on the other side, like we have like impact craters forming, and then collapse taking over and modifying the crater topography into the the chaotic terrains. So that's like that very simple stratigraphic arrangement,
Cool.
could provide an explanation that reconciles the existence of a global volatile rich layer, but regional or supra-regional expressions of collapse into chaotic terrains,
Yes.
and then like areas of exhumation and the formation of these glacier-like features.
Nice.
So now, like something really important here, like we're gonna go to, I think it's figure 4.
Figure 4. Let's
Yeah.
figure 4 after our illustration there. Sorry. Figure 4. 8.
Yeah.
I'll get there. 3 and 4. There we go.
Yeah. So here, like, so if we look at figure 4A,
Okay.
and we zoom into figure 4A, something that you're going to see here are these craters that appear to have like sublimation, peripheral sublimation generating the modes.
Okay.
These moded regions, right? Now,
Yes.
they happen, like, I mean, these features happen on Mars too, and like, when an impact happens, it produces like the uplift of the topography like this. So if the
Yep.
layers are like this originally, then the impact happens and they become tilted
Yes.
away from the impact rims, So like this is actually really interesting because this would actually suggest that we have a sublimation lag that is stable, that is not volatile ridge, like a refractory lag, and that beneath it you have this volatile layer.
Yes.
Now the impacts would actually, reorient the layers, and then sublimation would take over and produce these modes.
Yeah.
So the like so this brings up the whole questions of, if you have like, let's say, halite, and as like, for example, like some of my co-authors, like they consider that there could be other compounds as well that we're going to be assessing. It doesn't have to be halite. Okay, halite is the one that is consistent with the sublimation, and it's also consistent with like the flow rheology in the modeling. So it kind of like fits the bill, but we have to investigate other compounds. And
Yes. Sure.
for example, Jeff Cargill is one of my co-authors, is like assessing other possible compositions as well.
Yes.
So the question here is that you have these volatile materials that float on the surface of Mercury, but why are they not everywhere where you have impacts?
Fair question. Okay.
Yeah. So like, I mean, if it is true that the stratigraphy that we're talking about of having this basalt layer and then impacted, and you should see them everywhere, like pretty much, that's not the case, and also like how stable are they, so like this particular like set of glaciers, like they formed into like, I mean, this impact crater is thought to be about 1 billion years old, 1,000 million years old, and it still looks pretty pristine, But if we go to figure, okay, let me see. Oh yeah, the second figure in the supplementary material.
Okay.
Sorry.
It's all good. All good. Figure 2 in the supplementary. Here we go.
Oh,
yeah.
like actually, can you scroll down to the next one?
Then it goes down into the simulations.
Oh, all right. Sorry. So,
you
let
mean
me see here. Oh, maybe figure 6. Sorry, like,
yeah.
let me see.
All
Here,
good.
I'll check.
No, not 6.
Yeah, like it's kind of like difficult to keep track of all the figures in the, like, give me a second. Oh yeah, figure 6. Sorry, it's not in the supplements. Yeah.
Oh, it's not.
Yeah, figure 6, like the main. Yeah, like sorry about that. Yeah.
Good.
Yeah,
Good.
like.
I'm still
So
6. Here we go. Oh, nice. Okay.
yeah, that one there. Yeah, sorry. Like, so if we actually zoom up on it, so so this is the Eminescu crater. I think that's how you pronounce it. I think.
Yeah.
Like here you can see again the pig ring,
Yes.
and you can see these lobate
Yeah.
areas around the pig ring. In figure B, you see that that like they actually outline,
Oh,
like what appear to be depressed areas because you
yeah,
have like retreat of like these bright materials.
gotcha.
And so this actually is a very interesting figure. I mean, first of all, because it connects, like it shows further evidence of these lobate features. In this case, they are more weather eroded, resurfaced, So
Sure.
like you only have
Right.
the outline there, that
Mhm.
is essentially identical to the other set of like, glacier features that we were looking at before that are better preserved.
Very
So
nice.
my view is that these are basically resurfaced ones where the volatile phase is mostly gone,
Yeah.
So it could be because you have a thinner refractory layer, maybe because
Okay.
materials
Okay.
exposed are, like mostly volatile,
Uh,
and contain very little lithic in the big ring. But like, uh, but the big picture here is that like these glaciers could be metastable features. By
okay.
metastability, we mean that they could, in some cases, last a billion years. In other cases, they could just disappear,
Yeah.
over shorter timescales.
Sure.
So uh, it's not a solution; it's more a question. Like so the question here is, uh, I'm talking about future work, right? So like, are other craters, do they have a history of like exhumation of the volatile rich layer and the formation of these glacier-like, forms, landforms, but that they were completely removed,
Mm-hmm.
due to like their metastability or, more towards the spectrum of instability, and they are no longer there,
Yes.
you know?
Okay.
So that's something that needs to be investigated, you know? And yeah, it needs to be investigated and tested. My feeling is that that might actually be the case, but I haven't done the work yet. So then like there's another question here that another issue that I wanted to talk about, and if we are finding glacier-like features
Okay.
on Mercury, okay, why uh, is this important? Like, what is the large scale importance, like as far as solar system studies go?
Okay.
Like first, you know, um, like we stretch, like the glaciation as a phenomenon, like would stretch from like essentially Mercury all the way to Pluto, where we have nitrogen glaciers.
Ooh, 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 ooh. Okay.
you
Okay.
know so and you say, well, yeah, I mean there are different volatiles, but why would anybody care, like whether you have like glaciation throughout the solar system? And the answer to that could be that in general, like finding volatile phases are important, because of habitability, for example,
For example.
and like atmosphere, uh, like the connection to proto-atmospheres or like the generation of transient atmospheres. So finding volatile
Or the whole.
unstable volatiles at the surface of planetary surfaces is really interesting. And so glaciers or glacier-like features, like point us to areas in the crust where we have volatiles.
Yes.
We know you could have like you can go to Siberia, a permafrost area, right? And you could have desiccated permafrost that has no ice at all. Do you want to land there? Like if you wanted to like design a lander to go and investigate these volatiles,
Okay.
for whatever reason you're looking at atmospheres, habitability, like
Any of it.
whatever you want to investigate through these volatiles, you have to really choose the landing site well. You have to go to a place where there are surface expressions of these volatiles, and these are definitely surface expressions of their presence. The advantage of the glaciers in the case of Mercury over just hollows is that they are more extensive.
Okay.
So we can actually consider thinking in terms of landing something like larger areas that can also be dated
Fair.
more easily than individual hollows or hollow clusters,
Yeah.
because
Fair.
these glaciers are extensive. Areas that are modified by hollows are small, so it's very difficult to date them using
Ah,
craters. So there are numerous advantages here, to like identifying these glacier features. But
cool.
so this Okay, brings up to a really, really fundamental question.
Ooh, I like
And
those.
the question is, what is the origin of this volatile rich crust of Mercury? You
Okay.
know, we see, let's assume that what we're seeing are, you know, expressions of glaciation and expressions of like volatile losses in chaotic terrains. You know,
Let's assume.
that is a lot of like, you know, that's a lot of volatile. You know, and
Yes.
what is the age? So now we're gonna go to figure 8. Sorry, figure 8.
Figure 8, figure 7, figure 8. Ooh, okay.
Yeah. So I don't know if you remember, like in the first figure, Borealis chaos,
Uh-huh.
like figure
Yes.
1,
Yes.
that like we brought up this North Polar chaotic terrain, and
Mhm.
so this is what it looks like, okay, or like part of it, and the you'll see that. Can you close up on panel A?
Sure.
So you'll see that, for example, like the pointers 1,
Mm-hmm.
2,
Yes.
and 1 and 2, they actually indicate 1 is like this crater ring. It's like it's
Yeah.
this really large crater ring that like
Mhm.
doesn't fit entirely in the image, but you can see that the rim is disturbed. It has like this this gap. So
Inventory.
that crater is like about 150 kilometers across. That's a really large crater.
Yeah, it is.
Then the label 2 indicates a smaller crater that is also like
Okay, there it is.
disrupted by this
Yep.
discontinuity in the surface topography.
Yep.
And then
Yep.
in 3 is a really small crater about 10 kilometers across, where
Yeah.
you can see
Right here.
this disruption pattern.
Yep.
Then
Yep.
um, the so when you actually take, and you can see that the surface, can we go to like figure B
Sure.
to show you, like, because that's a close-up into figure A, and so you can see a little bit like higher resolution. So yeah, so here you see how it's interesting that this process of a surface disruption,
Okay.
merges because the crater, like the surface is heavily cratered. So when you start removing the rims, you start merging depressions, right? Like
Yes.
depression 1 there, and then depression 2 there, that is kind of like multiple, like, craters that actually became
Wiggly things.
like interconnected, and
Right.
then 3. So this interconnection, just because it's happening, um, like allows us to sort of like uh, define a base level of collapse, that
Okay.
can be measured. And that's what we show in the elevation profile.
Okay.
The base of collapse is very close to -4 kilometers.
Yes, right
Okay.
here. Mm-hmm.
Yeah.
Mm-hmm.
So then
Starting there.
there's a, yeah. So the question is, like, if you think about it, if you have irregular topography, like you have in this topographic profile, some ridges, some rims are high, others are low, but
Yes.
they all seem to collapse to the same base. To me, that indicates that there is a stratigraphic discontinuity.
Okay.
Like basically, like the base is the transition where like the materials become volatile free,
Yes.
or like
Yes.
the volatiles become stable.
Mm.
I think is the former. Something else that you will notice in these figures and the and other figures is that the large component, like the large craters, uh, all the large craters that you see in these landscapes, formed during the late heavy bombardment, are disrupted. There is, like, you can see a pristine superposition of craters, but they are all small, and they can be used to
Yes.
like date
Hey.
the
Mm-hmm.
end of resurfacing.
Yep.
Um,
Gator.
so this is kind of telling us that the materials that comprise this
There.
upper crust, like they were for an extended period of time
Yes.
unstable
Yes.
and pointing to a volatile rich composition. Okay, so which is the same case in all chaotic terrains, by the way. There is a much stronger case made morphologically in the 2020 paper, and
Okay.
therefore we didn't really go into the details here because it's basically repeating the same story. Like the morphologies are almost identical, except for this base of collapse. So
Cool.
now, if we go to figure 7,
8, we'll go up to figure 7, North Polar gravity.
Yeah, so that's a gravity, like a gravity map, like showing the outline of like borealis scales. Like this is from, is a reference to a paper that was published by some colleagues, and
Got it.
I find this paper to be like,
Yes.
I would say fundamental, actually. Like, they,
I like that.
it's very interesting. So they actually looked at these circular gravity anomalies and they interpreted them as buried basins, that became filled with lavas.
Okay.
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 So they
Okay.
they did count on this, proposed buried basins, and they got an age that is older than the late heavy bombardment. So the
Oh,
late heavy bombardment, like, that happened roughly about 3.8, 3.9 billion years ago, I think. Like is where, where you have all the surface craters, essentially. Like most of them. I mean, they're, younger ones, of course, but like most of the craters, like the large ones, like formed during the late heavy bombardment.
yeah.
On the moon, when you look at the surface of the moon, most of them like are, were produced in this period. But like there's some research that we cite in the paper indicating that there was a phase that happened before the late heavy bombardment,
Okay.
that that also produced dense impacting in the solar system, in the inner solar system.
Okay.
So those papers are referenced,
Okay.
and so now what we find is that, like, if you look at the square where we indicate the location of figure 8A, that's
Yep.
where we have the, like where we're looking at the chaotic terrains, and there is a buried, like one of these anomalies, one of these high anomalies, like lava filled basins or plains
Okay.
from the solder surface that was detected in the, by previous work. So like it may be that this interface, this depth of collapse, is controlled, where like the volatile rich layer encounters like these gravity detected paleo surfaces that are lava rich.
Yeah. Okay. Okay.
So the now the that would actually make sense in the sense that
Yeah.
we know that the formation of the chaotic terrains modified most of the late heavy bombardment craters. So the materials that were modified, they have to predate the late heavy bombardment.
Yes.
And so now, if these materials actually superpose, like, and they actually superpose this buried, impacted topography, it provides a very important constraint. Um, like the one of the if you think about the formation of a volatile rich layer on top of Mercury, you would think, well, maybe like the formation of like zonation in the mantle, like like producing kind of like a flotation crust, could do
Okay.
something like this, like it's being conceived in the past. But if you have a buried cratered surface,
Okay.
that is actually beneath the the volatile rich layer, this implies that its origin was not due to mantle differentiation. It must have been like a top-down process that buried the surface. Okay, that's a super important constraint.
Okay.
Yeah, because it gives us like a temporal framework. It tells us that it happened before the late heavy bombardment,
Right.
but after the formation of these buried basins that are gravity detected. Okay. So yeah, so there comes a connection to. I mean, the only thing that I can think of is, like as a top-down process, is the collapse of the proto-atmosphere.
Ooh.
Or,
Okay. Okay.
you know,
Yeah.
and
Yeah.
that's like
All right.
that's where it gets into,
Okay.
like where we need. I mean, there's a need of more work here,
Like,
because it gets into like very complicated modeling. In the article, though, I suggested a model that needs to be tested. It's like right now this is a conceptual model, but I think it's a fun model to think about. So, like, I'm just gonna put it out there. It is in the paper, and on Mars, like going back to Mars, we're talking about the hydrosphere of Mars. So
Yeah.
one of the key, like aspects of like the Martian geologic history is the presence of a buried hydrosphere. Okay,
Yes.
initially this hydrosphere like was proposed to have been captured into like a global mega regolith layer. So
Okay.
the mega regolith, as you know, is like during the late heavy bombardment, like you generate all this impact ejecta, and you fracture the crust, and you produce a high permeability upper crust. Like several kilometers deep.
Really? Okay. Okay.
So so for Mars, like a classic model by Clifford and Parker,
Yes.
they propose that this mega regolith, formed the storage domain for this Martian hydrosphere in the subsurface. Now, what is important here, like this is why I bring this up, is because the idea here goes, according to the literature, or this older literature, that like groundwater outbursts from this aquifer produce the Northern Ocean. So essentially, the mega regolith hydrosphere gave rise to the formation of the Northern Ocean. So there you have the connection between the subsurface, mega regolith, and the surface volatile rich layer that would be when the ocean freezes at a continental scale. Okay. So now, like the way that I extrapolate this concept to Mercury is the following. If this hypothesis that there was this earlier pre-late heavy bombardment phase on Mercury that produced these basins that we see in Figure 7, generated a mega regolith.
Okay.
It should have happened at a time when the planet was, highly volcanic. It was very early, very, very early, in the planet's history. So you would have a lot of like gassing from the interior, including like, water vapor, like all kind of like volatiles, that could have like recombined to form, like some of these compounds that we're like talking about. So then, like, what if these are early mega regoliths, like stored a lot of like these volatiles, and then some seismicity event generated, seismicity could be an impact, volcanism, generated a proto-atmosphere that was voluminous enough to cover the planet with, these materials that then were modified into chaotic terrain.
Okay, I'm with you.
So why is this concept interesting? Because of Mercury has the same gravity as Mars. So the compaction depth for the mega regolith should be similar, and so so it's worth considering, because it has an implication for exoplanets.
Indeed.
Okay.
Yep.
Yeah, like like a key question here is like, okay, if we have this volatile rich crust on Mercury, that we're working on right now, is it exceptional? Like, is it like the result of like rare processes that are highly unlikely and they just happen to happen, or is it the result of a process that is predictable and likely, So, like, if the process that I'm describing about the mega regolith, and it's one of many, there could be other processes, but this process, like, to me is interesting because I think would be likely to occur pretty much in many different planets. If like even exoplanets, you have a planet that is orbiting the parent star, at a close distance like Mercury, and it's likely that it's going to be like heavily impacted, and you're going to produce a mega regolith. It's likely that the mega regolith is going to be weathered by solar wind and produce a low permeability layer on top. It's likely that the planet is going to be degassing volatiles.
Yes.
And it's possible that this, the gassing could produce a trapped um, gaseous sphere in the subsurface, or
Right.
atmosphere, or like regolith sphere, or whatever you want to call it.
Right.
And it's likely or possible that like it would be metastable again, like this term, like not stable for a long duration,
Billions of years.
and that could connect it to like a proto-atmosphere. So that's like one of the implications there that I wanted to bring up. And
Cool.
so I think we've pretty much covered most of the paper.
Awesome. Awesome.
And that's a lot of information there. So
But it's very cool information. And
it's work in process,
just to
in
drive
progress.
just to drive it home, people, it's a paradigm shift. So, Alexis, I want to thank you so much for walking us through your very lovely PSJ article. Thank you.
Oh, thank you. I love talking about this, and if anybody has any questions, please reach out.
Okay. And you did touch on it a couple of times as we were walking through the article, and so I just want to push on it a little bit more. And where do you think we go from here, given the published article? Is there additional messenger data just sitting in the pipeline, waiting to be analyzed? Is there future missions going to Mercury that could maybe probe some of this? Is there additional theoretical work that could be done on the modeling of these impact ejecta and so on? So where do you think we go in the next few years?
Yeah, so actually, there are big questions that need to be addressed. I mentioned a few of them during the presentation. I'm very interested in this is it's a new idea,
Yeah.
that we're looking into right now. Okay, so it's it's work in progress. It might actually, end up being a feasible idea. It might not. We don't know. But I'm thinking that there may be an interaction between solar wind or high energy particles from the sun and the generation of the chaotic terrains. So here at Marshall now, at the Marshall Space Flight Center, I'm talking to some people who are experts in heliophysics, and so we're going to be examining this idea. So the basic concept is that, let me bring up the unknown, the mystery. The chaotic terrains are not really chaotic. They're organized. They are chaotic because they are messy, but they are organized because the rupture, the way that the surface is breaking up, is pattern. And the pattern is not just limited to one chaotic terrain, it's actually reproducible in you find that in almost all the chaotic terrains. It's these lineations, these really extensive lineations, hundreds of kilometers, extending hundreds of kilometers and cutting into a lot of craters of different diameters. And in many areas, you have a cross cutting of this lineated pattern. Okay. Cool. So it's almost like a crosswire, So the initially, I thought, well, this could be tectonic, but they're not tectonic because in areas where you remove the entire, where you see the complete removal of the chaotic terrain due to the collapse and sublimation because the materials go away, you don't see gravens. There is no evidence of gravens. And also because the pattern is repeated in areas that are thousands of kilometers away, including boreal scales. So what is producing a lineated pattern, in globally in Mercury's chaotic terrains? So it seems to be a top-down process. And my interest here is that maybe high energy particles like protons maybe could essentially remove the the volatiles from the surface like halide in an organized pattern if they are able to remain in a stable flow magnetic field line patterns, and so there are a lot of variables here. It's difficult to envisage because on Earth the aurora kind of are all over the place, but we're talking about a higher magnetic field than today,
Yeah,
today on Mercury,
big on it.
and very high energy particles that are rare,
Yes.
So in the early histories of the solar system. So anyways, that's a hypothesis that, is there in the pipeline. And
Cool.
if it works out, it would be pretty cool because,
Mhm.
it would be a connection between essentially heliophysics and
Yeah.
planetary landscapes.
That's always nice.
If it works out, because it might actually not work out,
Exactly.
like like I'm talking to some colleagues now, and they think that, what we have so far, the calculations and the observations are promising, but they have to be tested, and I'm definitely not an expert in magnetic fields and, high energy particles.
There are
But
people
it
who
would be
are.
a way of like making a very interesting, like, I'm working with people who are experts in the
Yeah.
field.
They make very interesting.
Yeah.
Be very cool. I seem to have lost my focus. There we go. Very cool.
Yeah, so that's like a direction that I'm interested in. And of course, I did a proposal, and that's a proposal now to like further the investigation to look at, like the evolution of the volatile rich crust on Mercury, the way that it collapses,
Yes.
like what we're talking about, but looking at the composition aspect, like considering other volatiles. And so yeah, there is a lot of like really interesting, promising work. Also, like from the modeling perspective, like, the whole concept of a proto-atmosphere generated by a regolith,
Yes.
that requires, like, again, multidisciplinary expertise,
Yes. That's
Yeah.
cool.
So, but because this is this is like an advance in front, so we really, we're always like thinking on, what the
Any
key
move.
questions are,
Very cool. Very cool. Well, it'd be
like to me,
Okay.
the key questions are like right now to me, it's like trying to kind of like connect like multiple fields of science
Mhm.
to get like, heliophysics and planetary surfaces and, astrobiology, like habitability, to sort of like produce an integrated view,
Yeah.
a broader view of what's going on.
Cool. Very nice. All righty. Well, Alexis, thank you once again for walking us through your very lovely article.
Oh, thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.